Hi everyone. From now, we will present our team project proposal. This is a content list of our presentation. In our proposal, we will talk about this paper. As you can see the title, this paper treats about graph neural networks. These days, many machine learning tasks such as object detection, machine translation, and speech recognition has been revolutionized by various end-to-end deep learning paradigms such as CNN, RNN, autoencoding. However, there are some engineering problems that are difficult to solve with existing deep learning technique. Social relation data or molecular structures are example of this. GNN has been studied for this, how to learn this graph structure, and this research has been actively conducted so far. What's graph? As you know, in the computer science field, the concept of graph is defined like picture above. In the graph structure, we can divide two factors to analyze this structure, edge and node. Each node and edges are expressed two kinds of metrics. One is adjacency metrics, which include adjacency information between nodes. The other is feature metrics, which include feature information of each node. These two elements are used for learning with weight and bias. When learning a specific node, neighboring nodes are aggregated and updated to the next hidden layers as shown in the figure above. GNN starts learning based on this procedure above. Through this GNN algorithm, we can predict the link, node classification, or graph classification.
As mentioned earlier, in GNN, it is important to aggregate information of neighbor node when obtaining the node's embedding vector. It is important to choose which neighbor and which aggregation function. Receptive field refers to the input area of neuron. In graph, the receptive field of one target node is equivalent to the subgraph that consists of node along path to the target node, and we can call it as receptive path. In graph, different nodes play different roles, thus it yields different receptive paths. Few of GNN approaches try to learn the meaningful paths that predict the propagation. This is the goal of our project, finding the mostly contributing receptive paths and designing effective aggregator functions. This receptive path will help us in node prediction tasks. We research three related works. In this work, the aggregation function is the sum of neighbors and normalization. Predefined normalization and no restriction on influence neighborhood. Graph Sage used the generalized aggregation, as you can see, and LSTM aggregator operates on a random permutation of node neighbors. Graph attention network use self-attention for GCNs. Attention coefficients indicate the importance of neighbor node features. This paper is our application target paper. There are contributions of this paper. They define function space for permutation invariant graph data, so they can assume the learning task is independent of the order of neighbors, and they propose adaptive receptive path layer with two complementary components. The GNPath has two functions. They define breadth function pi and depth function rho. In details, the adaptive breadth function pi assigns the importance of any one-hop neighbors by generalized linear attention operator, and the adaptive depth function rho use gate units. The gate units are used for extraction, newly useful signal or filtering useless signals or memorization. As such, they can filter the memory while extending the depth of the neighbor.
So let's talk about how we can improve this approach. As mentioned in previous slides, the main components of GeniPath framework includes two important functions, depth and breadth functions. These two functions are estimated as LSTM and graph attention network. So our first plan for improvement is simply change the architecture of depth and breadth function with transformer and graph transformer network. And our second strategy, we will apply the recently proposed legalization techniques for graph neural networks. In addition, we are also devising our own ideas to find the better receptive fields of the graph. There are no specific plans for it yet, but currently we are thinking about how to use the mutual information concept from information theory to solve this problem. And dataset, for datasets, we prepare four benchmark datasets and one real dataset. The Quora Citere form the citation graph dataset. Each node is a paper and edges a citation relationship between two papers. So these three datasets will be used under transductive learning setting. And for inductive setting, we will use protein-protein interaction dataset, the graph dataset of the graph data of protein molecule of human tissues. In addition, for real-world data, we have a KakaoTalk friend relation dataset. So in this dataset, each node is a user account, and edge means they have a friend relationship. The task is detecting the spam user accounts. And finally, this is our plan. Fortunately, our target paper has official implementation in their GitHub, so we will use it and focus on improvement of their work. So in next week, we will reproduce the original GeniPath result with our dataset by using their codes. And until progress updates presentation, we will change their model architecture, as I mentioned earlier, and apply regularization techniques separately. After that, if the performance increase, we will integrate two approaches into one model until the final presentation. So our final goal is submit our work to close data mining or machine learning conferences. So this is end of our proposal. Thank you for listening.